Hello and welcome to part 4 of our Introduction to High Performance Computing at NC State, specifically on our HPC cluster, Hazel. Today we're going over the true meat of HPC, which is the submission of parallel jobs. So when we last left off, we had submitted an admittedly small but very real job to our job scheduler LSF. This job required a single node, a very short wall time, and no appreciable amounts of memory. I was totally fine with the default 2 gigabytes that are set aside for each job. However, this is not really what, HPC is generally intended for. You're probably going to want to request a little more firepower to get done whatever you're trying to do on the HPC cluster. Before we dive into how to submit those jobs, let's get into what I mean by firepower. What terms can you use to describe the kind of infrastructure you need to perform complex computing calculations on a high-performance computing cluster? As you may recall from the previous segment, this is the general overarching structure of an HPC cluster. You have login nodes that allow users to access the cluster in general, and then compute nodes that are behind a firewall, with LSF as a job scheduler organizing access to the resources available on compute nodes, which are used to actually carry out computational tasks on the cluster. This is a general representation of the inside of a compute node. Obviously, this is an oversimplification, but this covers most of the core components you need to understand in order to utilize the resources effectively. Every compute node will have 2 identical processors, though different nodes can have different processors from each other, but in a given node, the processors will be identical. The processor, also known as the CPU or Central Processing Unit, is the hardware element that actually carries out the computations that a computer does. This is the brain of the computer, the thing that carries out operations. It does so by leveraging cores. These are the smallest hardware element capable of independently executing computational instructions. Essentially, if a thing is being done, it's being done by a core. Modern computational cores can make it look as though they're doing 2 things at once by rapidly switching between them, but for computationally intensive tasks, it's best to think of it as a single task being done by a core. Some nodes on our HPC cluster will also have a graphical processing unit, or GPU. This is a specialized processing unit originally identified for processing complex computational graphics, such as for videos or video games, but they've proven useful for extremely parallel tasks often related to machine learning and AI. Finally, every node has some amount of random access memory, often shortened to just memory. This is the physical structure on which rapidly read from and written to information is stored during active computational tasks. Everything that's run on a compute node is going to require at least 1 core and some amount of memory or RAM. And if a core is being used by one thing or memory is being used by one thing, it can't be used by another. The purpose of LSF, then, is to match jobs to the resources they need such that the entire infrastructure is used efficiently. For instance, if you have a job that's using 2 cores, a small amount of memory, and a GPU on this node, there's a lot of free resources that aren't being utilized. LSF might fit in an additional job that requires 2 cores and maybe a little more memory, or even a smaller memory job that requires a lot of computational power with 4 cores working together. So long as the resource requirements of these programs have been accurately given to LSF, these jobs will operate on the same node without interfering with one another. Jobs don't always fit in quite that nicely. For instance, you might have a job that requires only 1 core, like a serial job, but requires a large amount of memory. Even though there's additional computational infrastructure available, LSF will identify that there isn't sufficient memory for those jobs to run even if there are cores, and so it won't run it on this node. This is why it's really important to understand the computational resources required by whatever program you're going to run on the HPC, and then correctly translating these resources into something LSF can understand. LSF only knows what information you give it. It can't inherently understand what the computational requirements are of your program, and so if you misrepresent your program's needs, you'll end up either underutilizing the available infrastructure, or your program will try and use more resources than are available, slowing down or even crashing your program and other people's programs running on the same node. Of course, all of this hardware doesn't exist in isolation. The point is to do stuff with it. At the smallest level, computing is made up of threads, which are these small sequences of instructions that can be executed independently. Threads make up tasks, which is an isolated computational action and context running on a single core. I put isolated because they're more isolated than threads. Threads that are part of the same task are not as isolated from each other as threads that are part of different tasks. But there are means to make different tasks communicate to each other, which we'll get into a little bit more later in this part. A task is kind of an HPC specific term. You'll also hear the term process more broadly applied to, computing, and you might see the word process instead of task in the documentation for a program that you're trying to run on an HPC system. Tasks become jobs when submitted through a BSUB command and or job script, which can contain one task or more than one task. And they can be executed one at a time, which is a serial job, or they can be executed simultaneously, which makes the job a parallel job. So up until now, we've only really worked with serial jobs. That is, jobs that carry out a task in sequence. If you have 8 tasks you have to do, and you're running them serially, that means you're going to do task 1, wait until it's complete, then start task 2, wait till it's complete, then start task 3, etc., until task 8 is complete. All this is being done on a single core. However, our nodes generally are going to have more than one core, so that's a lot of computing power that you're kind of leaving on the table. Parallelization is taking tasks that don't need to be done in a specific order and performing them simultaneously. A task that is actively being carried out needs a core to itself, so multiple simultaneous tasks means multiple cores, and it can even mean multiple nodes working together. Parallelization can take 2 forms primarily. The first is shared memory. This is operating on a single node, but taking advantage of multiple cores at once. This does not need MPI, which stands for Message Passing Interface. MPI is software that's installed on every HPC system, and that allows nodes to communicate with each other. MPI must be built into programs or applications for multi-node jobs. Multi-node jobs also are known as distributed memory jobs. So this takes advantage of the cores on multiple nodes, but requires MPI to distribute those tasks since each individual node only has access to its own cores. MPI kind of serves as the bridge, organizing which tasks are going to what core, so that the individual computer doesn't have to. You can see here that this distributed memory job has 16 tasks, which in this case is more cores than any of these nodes have to themselves, but it can still carry them out all simultaneously using MPI. So after this, broad overview of what parallelization looks like and the kind of hardware systems you could potentially take advantage of, the question is, what resources does your specific program that you want to use on the HPC need? This is an important thing to figure out, because you want to avoid oversubscribing or undersubscribing your nodes whenever possible. Now, prescribing resources isn't always something you can do perfectly, but you can, at the very least, make a best effort for figuring out the kind of resources that your job needs before submitting it. The first step is to look into the documentation for the program you're trying to run, looking for phrases like the default number of threads, since generally each thread will require its own core, the default number of cores used, and especially how that number of cores is specified. Some programs will, by default, use a set number of cores, let's say 1 core, unless you explicitly let it know that it has more cores available. This means that even if your job requests 16 cores, if you don't let your program know that that's what's available, it'll still just use 1. On the other hand, other programs automatically detect the number of cores available on the node you're running, and automatically use however many cores are available. If you haven't specified that you need that many cores when you're running your job, you're going to be trying to use cores that other people already might be using and might be fully busy, slowing, again, both yourself down and other people down. You're going to want to look into the memory requirements for your program. This is especially important if you're running a serial job that only requires 1 core but requires a lot of memory, because LSF might schedule a large number of other users to take advantage of the available cores, so if you haven't specified that you need that memory, or you need the node all to yourself, then other users will start using up the memory that you need, even if it's theoretically available on that node. You'll want to look into whether your program incorporates MPI. We'll often call it Open MPI, as this will be necessary if you want to try and take advantage of multiple nodes at the same time. And you want to look for any other explicit hardware requirements, such as a specific GPU that's necessary, or OS requirements, such as a specific Linux distribution. If there is something like that that is different from the default Linux distribution installed on our HPC cluster, then you might need to build a specialized container to run your job. And finally, it's always a good idea to check whether there's any NC State specific or LSF specific documentation for running your program. If you're trying to run something on an HPC cluster, chances are somebody else has already tried to, and there may already be documentation that exists that helps you avoid, the common pitfalls, or just gives you a starting point to running your program on the cluster. So, let's say you've kind of dove into the documentation of your program of interest. You know what you need. How do you find the nodes that fit those needs? The HPC is made up of a bunch of different nodes with their own models, their own specialties. Some are older than others. Some have specialized hardware. How do you find the right node for you? Well, first off, there's a general rule. For computationally intensive tasks, you will want to run one simultaneous task per core. So if you're going to be running, let's say, 6 or 8 tasks at a time, that's how many cores you want to reserve. So your first step is to find nodes that have the right number of cores for what you need to run. Different computer models in the cluster have different processors and different numbers of cores. And one of the primary ways to check what the hardware specifications are for each node on the HPC, and essentially whether any of those meet your requirements, is through the command lshosts. Here you can see that I have logged in via terminal to the HPC cluster. I'm on login 02, and if I run lshosts, I get a lot of information about each node on the cluster. This is a lot of nodes. It can be a lot of work to look through. But you'll see here that each line contains the host name, the type of architecture, the model for your CPU, the memory available on the node, the total number of cores that that node has, and the specific resource tags. If you scroll down here, let's say we look at GPU GPU 07. You can see here that it has the GPU tag. This model name here gives you a starting point to look up the specific CPU if you need more specific information than just the number of cores and the amount of memory available. And this list of tags can be useful right here for identifying specific features of this node. Some particularly useful ones include GPU, which indicates that it has a GPU, as well as things like L40 or H100, which indicate the specific types of GPUs on that node. You'll note here that memory can vary wildly between the different nodes. This one here has about half a terabyte of memory, versus this is closer to 200 gigabytes. This one has 250 gigabytes. Just varies from node to node. This can be a useful place to start to just see what's available on the HPC. If you're looking for a specific type of GPU, let's say I need an H100 and you want to know how many are available, you can do something like this. Let's type clear to make it clear. lshosts grep H100. You can see that there are 4 nodes that have H100 GPUs. But if you have a program that could also take advantage of L40 GPUs, type in L40. You can see that there's a lot more L40 and L40S GPUs available, which means that you might have a bit shorter for wait time if you try and take advantage of the L40s instead of the higher-end H100 GPUs. Exactly what information from lshosts will be useful to you kind of depends on what your program needs, and it'll be something you figure out as you get more experience with the cluster. It might not be immediately clear what all those resource tags mean, so if you go to hpc.ncsu.edu, navigate to Running Jobs, and LSF Resources. HPC.ncsu documents LSF Resources if you're trying to get there quick. You can see what these resource types mean, and then you can look into whether your program needs any of these specific resource types or doesn't work with any of these specific resource types. You can see here this L40 is NVIDIA L40 GPU. There are a few other commands that can be useful for getting node specifications beyond lshosts. I generally recommend these if you're running into trouble and you're trying to figure out why something isn't working. The more information you have available, the easier it is to figure out what exactly is causing your issue. Just as an example, we're going to run an interactive job on a GPU node. So I'm quick. I went to the running jobs on the HPC page, and I am just copying over the GPU indicator because I often forget exactly what you're supposed to put there. And now I'm going to set up an interactive job on an HPC node. So BSUB-I, capital I, lowercase s to indicate that it's interactive, -Q, GPU, because I'm specifically looking for a GPU node. We're going to copy and paste that little GPU specifier that indicates how many GPUs you need access to and what mode you're going to be using it, essentially whether or not I'm okay with somebody else using the same GPU as me. I don't care because I'm not actually using it, so I'm going to click shared, as well as my wall time, -W of, let's say, 10 minutes, bash. So if we type ls hosts, and I search with the grep for the specific node that I'm on, which is GPU 02, I will see some information, including that I should have 24 cores, 376 gigabytes of memory, and the following resource tags, including that it's currently running RHEL 9 as a Linux distribution. If I run uname-a, you can see that I am running Linux, which is true, and this echoes the x86-64 architecture that we see under ls hosts. ls CPU gives you detailed information about the CPUs available, including that the CPUs have 12 cores for a total of 24 available. Free-mh tells me that I have approximately 380 gigabytes of memory, which matches what we saw under ls hosts. You'll sometimes see some slight discrepancies in the numbers due to either rounding errors or gigabytes versus gigabits, which are slightly different in terms of the final number that you'll see at the end, but they should be fairly close. If I run NVIDIA-SMI, it will print GPU-specific information, including that there is one GPU and it's not being used by anybody else. In this case, it is a GeForce RTX 2080, which if we run that ls hosts command again, you'll see that RTX 2080 tag indicating that this is in fact the correct information. And you can also look at specific files that correspond to, detailed information about specific aspects of this node. We're going to use less. We do etc os-release. You should see that it is Red Hat Enterprise Linux, which is RHEL version 9, which is why it said RHEL 9 as a little resource tag, as well as some other information. If you do less proc CPU info, which isn't technically looking at a file, but it kind of generates a file, you get some information about the CPUs. This is pretty in-depth, and I'm not going to go into the specifics, but you should see this same model specifications as when we looked at ls hosts. Let's see if we screw up and see if that's true. Gold 6126 does correctly reflect this gold 6126, which you could then, look up for more information. And kind of a similar deal for mem info. And you see this is in, kilobytes, so it's kind of hard to fully grasp this number, but should roughly correspond to what you've seen about the available memory. So all of those last three options, except for maybe OS release, are probably more detail than you're going to need for your typical day-to-day use of an HPC system. You might never even take a look at the node specifics, in all honesty. But this is a good place to start when things don't work. Figure out what node your job is running on, and then get as much information as you can about the node itself, and use that as your starting point for figuring out what exactly is going wrong, what might the incompatibility be, and how to solve your problem. Once you've determined what resources your program requires, and whether those resources are available on our HPC cluster, you can use the following BSUB specifications to make sure your job runs on the appropriate nodes. A BSUB-X gives you exclusive access to a node. This is useful if you know you want to be able to utilize all of the memory and have no risk of anyone else kind of intruding on your memory space. This can be useful if you're running things like certain R complex models where you'll need a lot of memory available and it'll fail if someone else potentially oversubscribes and uses more memory than they've reserved for themselves. This is also helpful if you're running a job that requires a lot of memory but doesn't require a lot of compute, as there's a risk that gets put on the same node as someone else who needs those cores that you've left available, but might use up the memory that you need access to. You can also just specify the amount of memory you need. This can be useful in making sure that you don't get put on a node that doesn't have enough memory, using -r usage, and specifying the amount of memory. This doesn't actually exclude other users from using that memory or really reserve it for you in any way, but it does help the job scheduler put people who need large amounts of memory on different nodes by making sure that the reserved memory doesn't add up to more than the total node memory. If you're using multiple cores, you will likely want to specify how many hosts you want those cores to be spread across. If you're running a shared memory job, you'll set span hosts equals 1. And if you're running a distributed memory job, you can use ptile to say how many cores you want per node. For instance, -n of 16 for a total of 16 cores, and ptile of 4 would be 4 cores per node. If you don't specify hosts or ptile, then LSF will kind of spread your cores over hosts as it sees fit based on its own scheduling parameters. So it's generally best if you have a need to specify what you need with hosts or ptile, but if you don't, then you might have less of a weight if you just allow LSF to fit you in where it makes the most sense. Finally, if you need a specific resource, you can't just run on any node. You need something that either has a specific GPU or one of the other resource types that were indicated with ls hosts. You use BSUB -R, like we've seen for R usage in span, but in this case you use select, and then you insert the specific resource tag that you want to run your job on. If you can use multiple options and you just want to make sure it's one of those, for instance, let's say your GPU code could run on an L40 or an L40S, you can use a pipe symbol, that kind of vertical line symbol, to separate the different options, and it'll run on a node that contains at least one of those resource types. So, now we've kind of dove into the conceptual framework of parallelization, as well as the two main types of parallelization on the HPC, which are shared memory and distributed memory. And we've gone over the basics of how to identify what resources you need, find whether those resources exist on a cluster, and specify those resources in a parallel job. Now let's do a little bit of an example to just kind of get our feet wet, get our toes in the water, and get comfortable submitting parallel jobs. I'm going to quickly navigate to this folder just to briefly walk you through the files here. We're not going to go in depth into the Python. It's fairly simple stuff, and you're welcome to check it out on your own time. But in brief, this is a folder with 7 files in it, including a run inputs.txt, which is just a list of animals in this case, but it could be any list of strings separated by line breaks, as well as a baseline mytask.py, which is a simple task that takes in an input text, simulates a duration, by default around 1 second, slightly modified to give some variability between your different tasks, identifies the host that's running this task, reverses the text to give you some kind of identifiable output, and returns that output. Fairly simple and straightforward. This is set up to run in parallel, either with a shared memory job, which is limited by how many cores you have on a node, or a distributed memory job, which integrates MPI, allowing you to orchestrate your tasks over multiple nodes. This also includes a split into batches.py helper function, which splits the tasks into batches for the distributed memory job. I've also created a starter submit shared.sh script for submitting the shared memory script, as well as a submit distributed.sh script, which is useful for submitting the distributed parallel.py Python script. So we're going to start with our first exercise, which is a shared memory example Python script. This means you would specify it using -r span brackets host equals 1, because you're only able to run shared memory jobs on a single host. However, this is going to use, it's a Python script, but it's going to use the multi-processing module, which means that it will be running on multiple cores, creating separate tasks or processes to split up the work amongst multiple cores and take advantage of the extra infrastructure. As your first step in running any kind of application on the HPC is to read up into the documentation. And this is a, fake example that doesn't actually have any real documentation. I'll give you a brief summary of what you found in quotes when looking through the documentation. You find that each thread or task reads in a string from an input file and prints the reverse. You're simulating a core-bound task, which means that you need one core for each task to operate effectively. The default number of threads is 1, which means it'll just run on one core by default. But you can increase the number of cores to the number of cores detected on the machine. Note that it doesn't mention anywhere that it limits the number of cores based on your, LSF or Slurm reservation, which means you should make sure that you're manually not, oversubscribing or undersubscribing. And there is no mention of MPI, so you can be fairly confident that this is a shared memory parallel application, but one meant to be run on a single node. So, if you remember from our previous segment, there's a fairly straightforward process for submitting a job, and we're going to do it together. In terms of submitting your job, the steps for submitting a serial job and a parallel job are actually very similar. It's really just the requirements that you're requesting that make the difference. Let's go through them together for this first exercise with a shared memory job. We're going to start by creating or modifying our batch script. Our starter code is located in /user/local/apps/sample/tutorial. I'm going to get rid of that backslash, so I copy the entire directory, not just the contents of the directory, which is what happens when you leave the slash. I'm going to copy it into my home directory, because that, as we've mentioned before, is a good spot for lightweight code, which is exactly what this is. Note the -r after the copy, because we're copying all of the contents of a directory, not just a single file. Now we're going to take a look at this submit shared script and see what we have to change to run it, and just see what it's doing in general. So let's do cd into tutorial and nano submit shared. You can see here that this starts as a typical batch script with -n equals 1, so this is just going to use one core by default, and span hosts equals 1. This is going to make sure that even if we increase n to beyond a single core, it stays on a single host. This is a shared memory job, so it needs to be on a single host. It's named shared. You can change the name to whatever you want. It's going to run for a maximum of 10 minutes, though it's going to be a lot faster than that in practicality. It is going to put the outputs for things that go well into shared out, followed by the job ID. And the errors for if anything goes wrong go into shared error, followed by the job ID. We have two arguments that we need to specify, or two variables we need to set: num tasks and num cores. Num tasks is how many tasks we want to carry out in total. This is using the simple inverse of a string function that we went over earlier, about how many we actually want to do, and how many cores we want to use. Once these variables are set, it runs a source script to set our environment, activating a Python local environment found in user local apps samples MPI4PY. Note that this says MPI4PY. That was just the basis name for a shared environment to run both of these exercises, and this particular Python script does not use MPI or MPI4PY at all. And then we're going to use Python to run the shared parallel.py script, specifying -t for this num tasks variable, and -b for batches is the number of cores. We're going to batch our tasks if we have more tasks than cores to have an even number of tasks spread over the number of cores available. We're going to modify this file so it now uses more than one core. In this case, let's just do 16 cores. We'll change the number of tasks to 16, so we're going to spread 16 tasks over 16 cores, which means they should all be able to be run simultaneously. And we'll make sure that num cores matches -n, which it does, and this job should be ready to be submitted. In our documentation, we didn't see any other hardware requirements. We know that we have a pre-set up Python environment here, so we should be good to go. So let's do Control X and Y to save. And our next step is navigate to our job submission directory. So let's navigate to /share/our group /user. I'm going to type pwd, which shows that I'm in the RFS group with my Unity ID, so I'm in the right place. I'm going to make a little test folder so that I can keep my job outputs organized. I'm going to call it make directory parallel. I spelled that weirdly. MV parallel to the actual spelling of parallel. And I'm going to cd into parallel. And now I'm in my job submission directory, which means any temporary files and any permanent outputs of my job will automatically be written to this Scratch directory, which means that it won't slow things down as it would if I was writing to, let's say, research storage or home. Next, we're going to submit our job using BSUB, followed by the less than sign and the name of our script. In this case, it is tutorial. Submit shared.sh. And we're going to run bjobs. And you can see that it's currently pending. And it's still pending. I'll give it a second. It's just looking for 16 cores available on the same node. Now it's still pending. Looks like it's a busy day on the cluster. And since I last checked, and this moment, it is now completed. Let's do ls and take a look at our error and output files. If we do lsslh, we can see that our error file is empty, which is always a great thing to see. That means that no errors were created. So let's take a look at our output file. We can see here that we did run 16 tasks, and they all were on the same C029 and 01 node that took in an input and produced an output, just as we expected. They each took around 1 second, which means that in theory, running 16 tasks plus this little simulated time for tasks that can't be parallelized would take us 18 seconds. But in reality, the job from start to finish after modules were loaded only took 3.668 seconds. This kind of shows the power of parallelization. The more you're able to effectively separate your tasks into completely distinct units that don't need to interact with each other, generally the more you can benefit from parallelization. But there are diminishing returns. I'll note here that even though each task only took 1 second, the tasks that can't be parallelized took 2.5 seconds. This means that we didn't have a final thing that took only, 1 second. It took about 3.6. In general, the longer that the tasks that can't be parallelized are relative to the tasks that can be parallelized, the less you're going to benefit from parallelization. However, this workload clearly benefits a lot from being parallelized and run on a, large number of cores node. Now that was a shared memory job, which is able to take advantage of all the cores that are on our single machine. But let's say we had more specific tasks to run simultaneously than we have cores that exist on any single node on the HPC cluster. Even if that isn't the case, let's say we want our job to not sit in the queue for a long time, which means we don't want to have to reserve an entire node for ourselves, and just want to be able to use, let's say, 64 cores wherever they might be. Once you start involving cores on multiple different nodes, it starts not being a shared memory problem and starts being a distributed memory problem. And for that, we need a solution that involves MPI. So for this second exercise, we are looking at a distributed memory multi-node application. And this one is intentionally designed to be able to run on whatever nodes are made available. This is going to be a Python script using the MPI4py module, but it runs the same task that we were running in exercise 1. It's just a simple read in an input and produce the reverse of that input. The summary of the documentation you found is that yes, each thread reads in a string from an input file and prints their reverse. It's simulating a core-bound task once again, 1 task per core, at least at one time. The default number of threads is going to be 1. However, the max threads are the number of lines in our input. It does not limit it to the number of reserved cores, and doesn't limit ourselves to the number of cores on a single machine. The script is run with MPI run, which means it requires MPI, which is our baseline requirement for knowing whether something is a distributed memory application. And now we're going to essentially try and do the same thing we did in exercise 1, but as a distributed memory job. And we're going to follow the same general steps that we followed before. We're going to start by modifying our job script. So nano, home directory, tutorial, submit, and in this case, distributed.sh. And you'll notice one main difference between our previous submit script and this one, which is this p-tile line. In this case, p-tile is cores per node. So we're going to change this to something that makes a little bit more sense. Let's say an n of 16. That's 16 total cores for 16 total tasks being run simultaneously. And we'll make p-tile 8. So we're splitting up those sets of tasks onto 2 different nodes, each having 8 cores. We'll change that number of tasks to be 16 so they'll all run simultaneously, and our number of cores to 16 because we want that to match our n up here. 2 quick things I'll note. 1, p-tile needs to be a number that can be evenly divided into this total n. You need to be able to split your cores into a number of groups that have this number of cores in them, so that way it can be split evenly over the different nodes. If you don't do that, it will fail into the job submission. So if I'm running 16, p-tile could technically be 16. If I wanted this to be a shared memory job, it could be 8, could be 4, or it could be 2. Technically could be 1, but you rarely want to make p-tile 1. One other thing I'll note is that this isn't just being run by Python anymore. We now have this interface of the MPI run -n for the number of cores, and then our application that has been built to integrate with MPI. This is a pretty common way to run distributed memory applications. And so if we do Control X and Y to save our changes, we can then do our next step, which is navigate to our job submission directory, which I am already in. /share /my group /my Unity ID, and then this little subdirectory I created. And we're going to go ahead and submit our job using BSUB > and the script that we've been editing. Submit distributed.sh. Click enter, and it's been submitted. These jobs are designed to complete pretty quickly, so if we run bjobs, see it's already done, which is great. We take a look at our outputs, which from our job script we would know are in our working directory. We can see that yes, we have 2 files, an error and an output file, and if we do ls-l, and we'll add tr to make it organized by date modified or time modified and in reverse. We'll see that our error file has 0 bytes, which is great. It means everything worked. There were no errors, and our output file is this one. If we take a look, you'll see first these ranks. Rank is an MPI term. That's how it divvies up these various tasks. And so if you have built an MPI application correctly, it can know from MPI what rank it is, and then you can use that to inform what tasks it carries out and how it interacts with other tasks based on their ranks. And if we look down here, we have our breakup of our tasks, and we can see instead of all being on the same host, our first 8 tasks are happening on this first host, and our second 8 tasks are happening on this second host. If we modify p-tile, nano, let's just do up to our previous nano command, because why do extra work? If we modify p-tile to a different number, let's say 4, this will now be 4 cores per node, 16 cores, total of 4 nodes, each with 4 cores. Control X, Y, enter. And if we repeat these same steps of submitting our job, taking a look at our job status, waiting till it's done, and now it's complete. And if we take a look at our output file, ls-ltr again, looking at our most recent output file, this number matches the number we see here. We can see that now, instead of 8 tasks being on one node, it's 4 tasks per node, and we're using 4 different nodes in this parallel script. And one thing I'll note, if your application doesn't require a specific number of cores per node, for instance, if each task is fully parallel and doesn't really interact with each other, and it just needs 1 core somewhere to run, you don't need to specify p-tile at all. We can delete this p-tile line, and LSF will just fit it in wherever there are available cores. It's this kind of logic that really differentiates the people that will more effectively use the HPC versus those who will just use it. understanding what resources your application needs, how to communicate those resource needs to LSF minimally so that you're only using the resources you actually need will make your jobs get picked up faster by the queue and finished faster than those who just kind of vaguely guess what resources their job needs. So we do Control X, Y, Enter. And actually, let's make this a little bit bigger. Instead of 16 cores, we can make this 64 cores, 64 tasks. This is something that would potentially take a little bit of time to get through the queue. But by not specifying p-tile, we make it a lot easier for LSF to fit it in, and then it gets picked up very quickly. And so if we BSUB once more, jobs, you can see that it's pending for a second, but it should get picked up quick. Now it's already running. And if I was trying to, let's say, get 64 cores on a single node, this would take a lot longer to run. It's running for a little bit longer. It should be done just about now. And it is. So we do ls-ltr. Take a look. We can see there's a lot more ranks, obviously, because there's a total of 64 ranks. And it's kind of a hodgepodge of how many jobs end up on a specific core. Sorry, how many jobs end up on a specific node. We can see here that the first node took 1, 2, 3, 4, 5, 6, 7, it looks like, cores. The second node had same number, coincidentally, of 7 cores. This third one had 8 cores, and this fourth one had 9 cores. And so it's really just, it found available cores quickly because those cores weren't being used by anything else. And because we didn't have any strict unnecessary requirements, the job was able to be picked up by the queue a lot faster than it would be if we'd kind of imposed those requirements. At this point, you should have everything you need to start experimenting on our HPC cluster with constructing and submitting your own jobs. Some final notes I'll leave as you try to endeavor on attempting something new, especially if you're trying something on the HPC cluster for the first time. If you're running into trouble, I'd first start by reading the documentation, both program-specific documentation for whatever you're trying to run, especially if they have an HPC-specific section, as well as the broader documentation at hpc.ncsu.edu. Documentation in general can be dense, dry, and sometimes out of date, but it's often the best place to just get your feet under you as you move forward trying to make things work. There's a lot of HPC documentation out there. I would recommend trying to find NC State documentation for whatever you're trying to do specifically, if it exists, or LSF-specific instructions if there isn't anything specific to our cluster. Clusters that run different job schedulers or just run at different universities can have different policies or just different ways of doing things that can conflict with how our cluster works. If you can, try to find working HPC examples from lab mates or other people in your department or other people at NC State trying to accomplish similar things to what you're doing. Starting from an example, even one only tangentially related to what you're doing, often makes it a lot easier to adapt to what you are trying to accomplish rather than building it from the ground up. Even working examples from other HPC clusters can be more useful than starting from nothing. If you're trying to run a new program and you're not 100% sure how it's going to operate, I recommend testing minimal examples using exclusive interactive jobs. This -I, lowercase s, and -x claims a whole node for yourself for an interactive shell session, letting you to try repeatedly different things, and as they break, you don't interfere with other people's jobs. You can confirm the behavior is what you expected using htop. As a quick example here, I have started an interactive job on a compute node using the following command, BSUB-I, lowercase s, -n of 1, because I only need a minimum of 1 core, but I'm going to claim the entire node, so it's okay that I'm only specifying 1, even though I might use more. -w of 30 and bash, but I'm already on this compute node, so I'm not going to run it. And then I have started the process of testing my script, so I'm printing what I expect my script to be, submit distributed. Oh no, we're going to test shared. So it's easier to test in the short term. And so I've already run this source to activate my Python environment. So now I'm going to run my Python script. -t of 1, -n of 1, but I'm going to increase the duration. Instead of a default of 1 second, it's going to be 10 seconds. And then this one's key. For testing purposes, I'm going to run it in the background using that little ampersand function. And you can see if I run htop, we're using 1 core, which is what we expect. And that was probably just the process starting, and I might run 1 core again. We got to exit 2, which looks like there might have been an error, so I'm going to run it again without running in the background. Oh, there it is. -b. And this is why you have an interactive job. That would have been a whole job that I'd have to check the outputs for. So we're going to try this again with the ampersand sign, and followed by htop. You can see that it's using 1 core to start the process, and then 1 core to actually run our calculations. I'm going to do that for about 10 seconds. Oh, that one will look chaotic because I tried to scroll. HTOP can be a little funky when you're running something that prints in between. So we know what worked the way we expected with the minimal example. Now if you ramp it up, let's say 16 into 16 batches for 10 seconds, click enter, and run. Give it a second to run that, and then run htop. You can see that now it's using, let's count them up. They're moving around, but 16 cores. So it is behaving as we expect. And we could try, let's quit this, we could try one more thing. Let's try changing the batches to 4, because we expect that to make it only use 4 cores instead of 16 cores, even though we're doing 16 tasks. And you can see that, yeah, it's using 4 cores now, which is what we expected. The specific cores being used might change from time to time, but in general, this shows us that the way we expect the script to behave is how it's actually behaving, which means we can kind of correctly predict if we increase the duration or if we increase the number of tasks we're trying to do or the number of batches we're trying to do it in, it'll behave as we expect. Outside of interactive jobs, you can still test minimal examples by just looking closely at the job outputs, or if you're building an application yourself or a script yourself, you can intentionally design outputs that clearly print exactly what's happening to make sure that things work on a minimal scale before you invest a lot of time or HPC resources into something that won't work. Finally, if you're running into trouble, ask for help. OIT_HPC at help.ncsu.edu is a great place to reach out for HPC specific questions. The HPC support staff would love to help you utilize their cluster. If your questions are about more broad research computing or data topics, or you're not exactly sure how to fit the power of the high-performance computing cluster into your research workflow, you can always reach out to the Research Facilitation Service at lib.ncsu.edu/rfs/contact us. I hope you enjoyed this tutorial, and if not, I hope at least you learned something new. With that, have a great day, and best of luck.